Right now, as you watch this, trillions upon trillions of quantum possibilities are dying around you every single second. Your coffee mug sitting on your desk isn't in two places at once. The chair you're sitting on isn't simultaneously existing and not existing. You've never walked through a wall, even though quantum mechanics says you should be able to. Something is killing quantum weirdness the instant it tries to touch our everyday world, and that something has a name: decoherence. Let's start with what quantum mechanics promises us, a reality so bizarre it sounds like science fiction. Individual electrons in experiments build up interference patterns one particle at a time, suggesting each electron somehow passes through multiple paths simultaneously. Particles separated by vast distances instantly know what's happening to their partners. Measuring one entangled particle can instantaneously influence another regardless of distance. This isn't speculation. This is verified, repeatedly tested reality. The double-slit experiment proves it beautifully. Fire electrons one by one through two slits. Common sense says each electron goes through one slit or the other. But watch what happens on the detector screen behind them. The electrons don't pile up in two clumps like bullets would. They create an interference pattern, bands of light and dark, like waves canceling and reinforcing each other. Electrons arrive one at a time, yet exhibit wave interference, a phenomenon unexplainable in classical mechanics. Here's the truly mind-bending part. This happens even when you send electrons through one at a time, with seconds between each launch. There's no chance they're bumping into each other. Each electron is interfering with itself. It's somehow taking both paths simultaneously. This is quantum superposition, and it gets weirder. Change the experiment slightly. Place detectors at the slits to see which path each electron actually takes. The interference pattern vanishes instantly. The electrons go back to behaving like normal particles, piling up in two predictable clumps. The act of observation changes reality. Now scale this up. If electrons can be in two places at once, why can't your phone? Why can't you? The equations of quantum mechanics apply to everything, from electrons to elephants. There's nothing in the math that says quantum weirdness should stop at any particular size. Erwin Schrödinger captured this absurdity perfectly with his famous cat thought experiment. Put a cat in a box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers and releases the poison. According to quantum mechanics, before you open the box, the atom exists in a superposition, both decayed and not decayed simultaneously. And if the atom is in superposition, then the detector is in superposition, and therefore the cat itself is both alive and dead at the same time. Schrödinger wasn't trying to explain quantum mechanics with this experiment. He was trying to show how ridiculous it seemed when applied to everyday objects. But here's the question that should haunt you. Why don't we see this? Why isn't your reality constantly splitting into quantum parallel universes? Why does the macroscopic world behave so predictably, so classically, when it's supposedly built from quantum parts that can exist in multiple states simultaneously? The answer isn't that quantum mechanics is wrong. It's spectacularly successful at predicting experimental results. The answer is that there's an invisible process constantly murdering quantum phenomena before they can manifest at human scales. That process is decoherence, and understanding it changes everything. Imagine you're trying to create a perfect quantum superposition with a single electron. You place it in an isolated chamber, pump out every air molecule, shield it from electromagnetic radiation, cool everything to near absolute zero. You've created a quantum island, protected from the outside world. In this pristine environment, your electron can remain in superposition. It can genuinely be in two places at once, spinning both up and down, existing in that spooky quantum twilight that makes physicists famous. Now add a single photon, just one particle of light bouncing off your electron. That photon carries information about which state your electron is in. The photon has now become entangled with your electron. Environmental interactions entangle the quantum system with countless degrees of freedom, rapidly suppressing superposition and forcing it into a mixed state that mimics classical behavior. The superposition doesn't collapse into one state or the other, not exactly. Instead, it gets smeared out across the environment. The quantum information that made your electron special is still there, technically, but it's now dispersed across that photon and everything that photon subsequently interacts with. Your electron looks like it's in one definite state now. The quantum magic is gone. This is decoherence, and it happens absurdly fast. Decoherence occurs on incredibly short timescales, often in femtoseconds. That's 1/millionth of 1/billionth of a second. In the time it takes light to travel the width of a bacterium, decoherence has already destroyed any macroscopic quantum superposition you tried to create. Think about Schrödinger's cat again. The moment that radioactive atom decays or doesn't decay, it doesn't stay in perfect isolation. The detector device is right there, full of billions upon billions of atoms. Air molecules in the box are bouncing around. Photons are flying in every direction. Decoherence is the process by which a quantum system loses quantum properties due to interactions with its environment through various mechanisms. The atom's state gets entangled with the detector. The detector gets entangled with the air molecules. The air molecules get entangled with the box walls. Within a fraction of a second, the quantum information has leaked irreversibly into an ocean of environmental degrees of freedom. The cat was never in superposition. Not really. By the time we opened the box, decoherence killed any quantum ambiguity long ago. The cat has been definitely alive, or definitely dead the entire time. We were just finding out which one. This is why you don't quantum tunnel through walls. This is why your coffee mug stays in one place. This is why reality looks classical despite being built from quantum parts. Every interaction with the environment acts like a measurement, constantly collapsing possibilities into actualities before your brain could ever register them. If decoherence destroys quantum effects so efficiently, how did we ever discover quantum mechanics in the first place? The answer? We got extremely good at isolation. Early quantum experiments worked with individual atoms and photons in carefully controlled environments. Fire a single photon through a vacuum. It barely interacts with anything, so its quantum properties persist long enough to measure. Trap a single ion in an electromagnetic field in an ultra-high vacuum chamber, and you can preserve its quantum state for seconds, an eternity in quantum terms. But try to scale up, and decoherence becomes your worst enemy. This is the central challenge of quantum computing. Every quantum system has a characteristic coherence time, the time over which quantum information can be reliably maintained. Build a quantum computer with superconducting circuits, and IBM's quantum computers with over 400 qubits in 2025 achieve coherence times around 100 microseconds. 100 microseconds. That's 0.001 seconds. Your quantum computer has to complete its entire calculation, including all the quantum operations, all the entanglement, all the parallel processing across superposed states, before decoherence kills it. This creates a race against time. Quantum algorithms must complete before decoherence sets in, and it gets worse as you scale up. Add more qubits, and you add more opportunities for environmental interaction. Even in ultra-cold environments, tiny vibrations, residual electromagnetic radiation, or interactions with surrounding materials can cause energy relaxation and defacing. This is why we keep quantum computers at temperatures colder than outer space, why we shield them with layers upon layers of protection, why quantum computer facilities look like something from a science fiction movie. Giant chandelier-like structures hanging in isolated chambers, maintained at millikelvin temperatures. We're not just building computers, we're building fortresses against decoherence. And even then, we're losing. But here's where it gets interesting. Scientists aren't just defending against decoherence anymore. They're trying to understand it at a fundamental level. Because decoherence might not just be the enemy of quantum computing. It might be the reason you exist at all. Here's a question that should keep you awake at night. Why does the universe have definite outcomes? Quantum mechanics, left to itself, doesn't make choices. The Schrödinger equation evolves probabilities smoothly and continuously. All possibilities remain possible, forever, getting more and more entangled in an ever-growing web of quantum correlations. If quantum mechanics were the only rule, the universe would be a static blob of unrealized potential. Every possibility would remain equally real, frozen in superposition. Nothing would ever actually happen. But obviously, things happen. You exist. You're reading this. History has a definite past. Your present feels concrete. Something breaks the quantum symmetry and forces the universe to commit. The traditional answer was wave function collapse, the idea that measurement mysteriously causes all possibilities to crystallize into one outcome. But that's not an explanation. That's just naming the mystery and calling it solved. Decoherence offers something different. It doesn't add collapse as a special rule. Instead, it shows how collapse emerges naturally from quantum mechanics itself when you include the environment. Think about what happens when a quantum system interacts with a huge environment. After decoherence suppresses quantum superpositions, the system remains in a mixture of possible outcomes, but coherence between them is destroyed. For all practical purposes, the superposition is gone. Reality has effectively chosen. Not because of some mystical collapse mechanism, not because consciousness observed it, simply because information leaked into the environment so thoroughly that the different possibilities can never interfere with each other again. This is called einselection, environment-induced selection. The environment doesn't just destroy superpositions randomly, it preferentially destroys certain superpositions while leaving others relatively stable. The surviving states are called pointer states. They're the states that best resist decoherence. And here's the kicker. These pointer states are exactly what we call classical properties: position, momentum, spin orientation. The stuff reality seems to be made of. Classical physics emerges from quantum physics through decoherence. Decoherence plays a pivotal role in explaining why quantum effects vanish in macroscopic systems. and how quantum states lose coherence through environmental interactions. You're not separate from the quantum world. You're part of it, but you're such a big, complex environment interacting part that decoherence happens to you constantly, every femtosecond, in every one of your atoms. You're locked into experiencing only those pointer states that survive environmental scrutiny. Decoherence isn't destroying reality, it's creating it, or at least creating the appearance of a single classical reality from an underlying quantum multiplicity. But wait, if decoherence explains why we see definite outcomes, if it explains why the world looks classical, if it's so fundamental to reality itself, then we have a new problem. Decoherence still doesn't actually solve the measurement problem. Not completely. Here's why. Decoherence explains why different quantum possibilities stop interfering with each other. It explains why superpositions become mixtures. It explains the appearance of wave function collapse. But it doesn't explain why you experience one particular outcome and not the others. After the basis is chosen and quantum superpositions are suppressed, the system still remains in a mixture of possible outcomes. And decoherence does not tell how and why only one of these outcomes is measured. Go back to Schrödinger's cat. Decoherence explains why the cat isn't in observable superposition. The environment destroyed that almost instantly. But the quantum formalism still describes both outcomes, a live cat plus environment state A and dead cat plus environment state B. Both are there in the mathematics. You open the box, you see a living cat. But why that outcome specifically? Why not the other one? The equations don't prefer one over the other. This is where different interpretations of quantum mechanics diverge. The Copenhagen interpretation just declares that measurement causes collapse. The wave function chooses randomly according to the Born rule, and that's that. Don't ask deeper questions about what measurement is or why it's special. The many worlds interpretation says both outcomes happen. And when you open that box, you become entangled with the cat plus environment system. One version of you sees the live cat. Another version sees the dead cat. Both exist in separate branches of reality. Decoherence is what separates these branches, making them unable to interfere, creating the illusion that only one outcome occurred. Collapse theories add actual randomness to the Schrödinger equation itself. Spontaneous collapses triggered by mass or complexity, making definite outcomes physical rather than just apparent. Quantum mechanics specialists gave 3 entirely distinct answers to the measurement problem at a 2024 World Science Festival event hosted by Brian Greene. Nearly a century after quantum mechanics was formulated, physicists still fundamentally disagree about what it means. And decoherence, for all its explanatory power, doesn't settle the debate. It just sharpens it. But here's where this story gets fascinating. The same decoherence that limits quantum computers, that destroys quantum possibilities, that forces reality to look classical, we're learning to fight it. Scientists are extending coherence times. Recent research has achieved coherence records ranging from 0.4 milliseconds in transmuns to over 1 minute in nitrogen vacancy spin memories. That's a factor of 10 million improvement in just one specific system. They're developing quantum error correction codes that can detect and fix errors caused by decoherence without destroying the quantum information. They're building decoherence-free subspaces, special quantum states that are immune to certain types of environmental noise. The 2025 Nobel Prize recognized Clark, Devoret, and Martinis for demonstrating that quantum coherence could persist in macroscopic systems with billions of electrons behaving cooperatively. They proved quantum mechanics isn't confined to the atomic realm. It can be engineered at observable scales. We're not just studying decoherence anymore. We're weaponizing our understanding of it. Because here's the thing. If you truly understand your enemy, sometimes you can make them fight for you. Decoherence is the invisible assassin of quantum weirdness. It's why your reality looks solid, predictable, classical. It's why you've never seen a cat both alive and dead. It's why quantum computing is so incredibly difficult. But it's also why you can exist at all. Why the universe has a history, why experience is possible. Without decoherence, reality would be a frozen superposition of every possible configuration, experiencing nothing, deciding nothing, being nothing definite. We live in the ruins of quantum possibilities. Every object around you, every moment of your experience, is built on the corpses of countless quantum states that could have been but weren't, killed by decoherence before they could fully manifest. The universe didn't choose simplicity, it chose complexity. And complexity means interaction, and interaction means decoherence. And decoherence means us, observing, experiencing, existing in what looks like one definite reality. But don't forget, we're still quantum at the core. Decoherence doesn't destroy the quantum foundation, it just hides it, obscures it, makes it practically inaccessible. The weirdness is still there, beneath everything, ready to emerge the moment we create the right conditions of isolation. The quantum world didn't go anywhere. It's right here. It always has been. We're just too big, too warm, too entangled with our environment to see it directly. And for now, in this moment, in this branch of reality, if that's what this is, that's probably okay. Because if we could see the full quantum truth, if decoherence suddenly stopped working, we might not be able to think thoughts, make choices, or exist as coherent conscious beings at all. Sometimes the enemy that defeats you is also the thing that defines you. That's decoherence, the invisible force that killed the quantum multiverse you could have lived in and created the classical universe you do. Essential, then as conquered frontier, creating natural curiosity loops throughout,